Hello everyone. I'm recording this video because I want to provide the medical class for the canceled class. So the October 1st class was canceled because the Korean government designated the the October 1st as the public holiday. So instantly. So even though the class was canceled, but we need to provide the maker class, right? So so I'm recording, and then uh, unfortunately, so my throat condition, so my health condition is not good now. So I have a sore throat. So so I think that my voice is not good now, but I'm recording. So I think I need to record the this class. So sorry about that, but I hope you can understand my speaking. So let's start. Okay, so I provide the second lab assignment. Okay, so actually we we missed the two classes in this week, and then so I believe the student need to perform the second lab assignment actually. So we are learning about the instructions, the it means so we are learning about RISC-V instruction set architecture. So and then I believe you need to understand how the high-level language codes are translated into the RISC-V instructions. So actually, so the instructions are machine codes, so which means that the instructions are represented using digital signals. But so actually, so but these machine instructions can be also translated into assembly instructions, right? So compiler. So as we learned in the previous class, compilers translate the high-level language code into machine code. So I hope uh, in the second lab assignment, I hope students can practice how compilers work. Okay, so I hope students can explore how compilers work. So it means that so high-level language code like the C code can be compiled with RISC-V compiler. Okay, so but so if we, so I believe you took the programming language courses, right? So 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 I believe so as a computer engineering student, I believe you practice the C programming, right? And that, but actually we can compile the C code, the C source code on the on our desktop computers or our laptop computers, right? But the actually if you are using Windows operating systems, I believe most of you are using x86 computers, right? So it means that the CPU, the the CPU, so Intel CPUs or AMD CPUs actually use x86 ISA instruction set architecture. So if you compile your the C code on this x86 machine, then the the compiler generate the machine instructions included in x86 ISA. So it generates x86 instructions. But we are learning about RISC-V, right? So we are learning about RISC-V instructions. So actually in this lab assignment, so we will practice the RISC-V compilers, so which means that we will use RISC-V compilers. But think about it. We are not using RISC-V processors, right? So what does that mean? So if we run a C compiler, then this C compiler will generate x86 instructions, not RISC-V instructions, right? Right? So actually for this lab assignment, we will use cross compiler. So you can find the cross compiler toolchain here. So cross compiler means that on on a different ISA platforms, such as, so in this example, we are using x86 CPUs. So on the x86 CPUs, this cross compilers compiles the C code to generate other ISA instructions. So for example, so in this lab assignment, we will use RISC-V cross compiler running on x86 CPUs, right? So cross compiler, it is working on x86 CPU, but when a C code is compiled, so compiled by RISC-V cross compiler, so compiler, then it will generate RISC-V binary file. And then this RISC-V binary file includes RISC-V instructions, right? So using a cross compiler, then we can generate different the machine code or binary files for uh, different ISA, different instruction set architecture. But how can we execute this binary file? And then, as I mentioned, we do not have RISC-V processors. We do not have RISC-V computers, right? So if you execute the RISC-V binary file on your x86 machine, then it will return errors. Okay, it cannot be executed. It cannot be executed on your computers. It cannot be executed on x86 machine. Also, it cannot be executed on ARM machines. Okay, so in order to execute this RISC-V binary file, then we will use a simulator. Okay, it's a simulator, and we will use RISC-V ISA simulator called Spike. So it's a simulator. It's not a real hardware, right? So it's just a software, but it it just emulate the behavior of a RISC-V processor, right? So and then it execute the RISC-V instructions, and then it just updates some architectural states in software, right? So what are architectural states? Like register file, registers, and main memory, right? Right. So if instructions are executed, registers and main memory are updated, right? So this simulator just updates the data. So it's just some software data, like some indexes, so the arrays, right? So it just updates the some registers, and then some main memory, but these are all software data. It's arrays, okay? So it just emulate the behavior of RISC-V processors. Okay, so actually for this project, not the project. So actually for this lab assignment, then you can follow the instructions in this lab document. But so actually for this purpose, you need to compile. So you need to build a RISC-V cross compiler, and then but it requires uh, a large amount of the other source files. Okay, so as I mentioned, where is it? So actually, so you may require a larger than 20 gigabyte for this virtual machine hard disk space or storage space. Okay, so it is because actually if for uh, in order to build the RISC-V cross compiler toolchain, then it requires the other uh, repositories. Okay, so actually, so the other large repositories from GitHub. So so you need to actually clone some other GitHub repositories, and then these repositories are used for building the RISC-V cross compiler, right? So so just to remember that your virtual machine storage require larger than 20 gigabyte. Okay, just okay. So you can just follow the instructions, right? And then if you build this RISC-V cross compiler, then this folder will be generated on your virtual machine. Okay, so Ubuntu or your Ubuntu virtual machine, right? Then also you need to build the RISC-V ISA simulator called Spike. Okay, and then also you need to build the the the, the kernel is a very simple kernel. Okay, so it's a PK kernel. So this RISC-V PK also needs to be uh, compiled. Okay, it should be built. Okay, then you can write the high-level language code like the hello.c, like this one, and then you can compile using RISC-V cross compiler. So this is the command for the RISC-V cross compiler. So also you can find the architecture IV32I. So we are learning about the IV32I instruction set of RISC-V, right? Okay. Then you can generate the binary file hello. Okay, and then using Spike to we build Spike in this lab, and then using Spike, then you can also execute the hello. Okay, so and then in order to execute the hello, also you need to use the so RISC-V PK. Okay, then you can find the output of hello is a binary file. Okay, and then if we use minus capital S option for the this RISC-V compiler, then you can generate an assembly code from the source code. And also you can use this command. That this is the object dump command. And then using this command, then you can also extract some information from the binary file. Okay, so then you can also observe the RISC-V instructions. Also, you can observe some data stored in the binary file. Okay, so you can this example shows that from the binary file hello, then hello.dump is is extracted using this object dump command. Okay, then you can observe the content of the hello.dump here. So this is just a practice. Then in this lab, then you can just compile this example code, and then you can so using the RISC-V cross compiler, you can generate the RISC-V binary file, and then using a dump command, object dump command, then you can also observe some information from RISC-V binary file. Okay, so if you see that text section in the dump file, then you can also find this is the RISC-V assembly instructions, and then what is this? This is PC. It's a program counter for the machine instructions. Okay, so this is the equivalent instruction, right? So I showed this this machine code instructions during the class, right? So this example shows that the PC of the main function, that is the first instructions. First instruction in the main function is the PC of the first instruction in the main function is 000100074, right? Then using Spike is a RISC-V ISA simulator, then we can also execute this binary file, right? So in the Spike, you can use the help command. So this is the in interactive debug mode, right? Interactive debug mode. Okay, so, and then using the help command, you can also list some commands supported by Spike. So using the until command, then it just executes the program counter value 10074. But actually, firstly, the Spike execute the program loader is a proxy kernel, it's a PK, RISC-V PK. So actually, if you just execute until the 10074, then actually the PK will be executed. Then you need to then you need to run one instruction after that, and then you need to repeat the until PC 0 0 x 00 10074. So this means that the Spike will execute until the PC, okay, again. Then it will approach to the PC of the main function, okay? Then, so if you execute the RISC-V instructions until the end of the main function, then you can like the learn 41 that means it execute 41 instructions, right? 41 instructions, okay? Then you can observe the values in register file, okay? So you can find the ABI name of the registers, RISC-V registers, and then so in this example, you can find that the final result is stored in the A0 and A5, okay? So as I mentioned, the purpose of this lab assignment is to make you explore the, the the compiler. So the what compilers do in the computer systems. Okay. So and then also I hope you can understand how instructions are executed by CPU, right? And then also by using compilers, you can generate assembly code. Also, you can extract the machine codes from the binary file, right? And then also you can compare the binary files. Okay. So the first task is to write the very simple code. So you can use your name, not my name. Okay. And then also you can compile some different version of this array sum. Okay. Then you can compare the generated machine code or generated assembly code for the different version of this accumulation code. Okay. Uh, so actually in this lab, so you need to you need to build you need to build the RISC-V cross compiler, and then you need to build the RISC-V ISA simulator. Also, you need to build the RISC-V proxy kernel. Okay. So sometimes you can encounter some errors. Okay. So actually, though, you can just follow the instructions. Okay. But if you encounter some errors, then you can just ask questions on Piazza. Also, you can get help from TAs. Okay. Okay. Yeah. Okay. So I hope everyone can complete the second lab assignment. Okay. So what did we learn in the previous class? So we learned about the operands of instructions, right? So there are three types of operands, like registers, memory, and constant. And then I mentioned that the constants are also called immediate, right? So most instructions, like arithmetic instructions or logical instructions, use register data as their operands, right? And then I mentioned that the RISC-V includes the Dorit general purpose registers and one program counter register. Okay, so it's called the PC. Okay, and then so this is the example. So the high-level language code is compiled, then the assembly code is generated, right? And then so the generated assembly code includes instructions. So you can find that this add instruction uses the register data, the data in registers as its operands, right? So we can use the immediate, so it's a small constant, immediate value. Also, so this immediate value is included in the instruction. So in the previous example, so you can find that, so it's a PC value like 0x1000, and then also you can find the machine code instructions like F blah 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 F. So I mentioned that this is the 32-bit binary data. So I mentioned that immediate value can be included in the instruction, right? So it means this machine code includes immediate value. Okay, so if a CPU reads this machine instruction that includes immediate value, then CPU can figure out this immediate value from the instruction. That's the meaning of so the immediate value is included in an instruction. Okay, and we also learn how the immediate values are encoded into the machine instruction or machine code. Okay. So we learned about the memory instruction, and then I mentioned that there are two types of memory instructions. It's a load instruction and store instruction, right? For the load instruction just transfer data from main memory to register, and then store instruction. The direction is opposite, so which means that the data from registers are transferred to the main memory, right? So, and then I mentioned that the most computers use byte addressable memory, so which means the byte address 1 occupies 1 byte of memory space, right? Okay, so this is the example, okay, and then also we learned how also the array data is translated. So the store instructions or load instruction includes the offset. So using the offset, so we can calculate the target address in the memory, right? Like so base so base comes from the registers like the x x0 or x1 or like register, and then using the data in this register, then we can add the offset. So offset is the immediate value. Okay. So immediate is a small constant. So immediate value is also including this load instruction. Okay. So so we learned how this array, the address of this array data is calculated. Okay. Okay, so let's see the C code example. So actually in this course, I frequently use the operator and, okay, so in front of variable name, okay. So what's the meaning of this operator in C, like A, like, or B? So actually, I believe if you learned about the C programming, then I believe you learned that this operator is the point operator. So it means that it represents the pointer of this variable. So actually, in what is the pointer? Pointer is, so you can understand that the pointer is the address of a variable. So what is different? So in this example, so A is declared here. So variable A is declared as integer type, right? And then the value of this variable is initialized as 0. So what does that mean? If a variable is declared, and then this is the integer type, and then I mentioned that the integer type, the size of integer type is 4 byte, right? So if a variable is declared, then the memory space is assigned to this variable, right? And then the type of this variable A is an integer type, so it means 4 byte of memory space is allocated to variable A. Okay, so A is in the main memory. What does it mean? So A also can be pointed using address. So if we use this AND operator like A, so it represents the address of A. So in this course, I frequently use the like A, so it means to represent the address of a variable. So in this example, the first printf statement, it print out, it displays value 0 because A includes the data 0, right? But how about this one? So this is the address of A, and then this is the integer type, right? But I use the AND operator. So it represents the pointer of A. So actually it's the address of A. So this is another example also in the array type. So you can also store some data to each element in an array, right? And then also you can represent the address of array using AND operator. So I mentioned that. So it's a B0. So and then it's a B1 and B2. Okay. So array is stored in memory like this. And then the type of this array is an integer type. So what does that mean? The size of each element is 4 byte, right? It's a 4 byte. So in the memory space, B0 is allocated, and then it's a 4 byte of memory is allocated to B0. And then for the next address, B1 is allocated. And then what is the size of B1? This is also 4 byte, right? Then what is the difference of address between B0 and B1? Obviously 4, right? So that's why we can calculate the address of B1 from the B0, right? So if we just handle the array data on array data, then we can provide the base address and the size of each element, right? So it means the base address of an array is the of B. The B is the array, right? Actually, it's the address of B0, right? Then what is the address of B1? Address of B1 is the base address plus 4, right? So why? The size of this element of array is 4. So it's an integer type, right? So we can calculate the address of the array element like this, right? So I hope you can understand this. Okay, so register versus memory. So we can compare the register and memory. So registers are faster. Okay, as I mentioned, the size of a register is very, very small, and then smaller. If the size is small, then it's faster. Okay, so that's why the processors include registers, and then say most instructions, like most arithmetic instructions, logical instructions. So and then also the control instructions actually access data in registers. Right? So we want to execute instructions fast, right? But we cannot store all of our data in the registers because the size is extremely small. So we store the data in the main memory, right? Then we need to transfer. We need to transfer data from main memory to the register. Also, the result by instructions also needs to be updated to the memory. So memory instructions transfer data from main memory to the register, or the data from register to main memory, right? So compilers manage the actually registers. Okay, so I believe so. In the second lab assignment, that you can observe in the high level language code is compiled. Then compilers assign registers to registers, right? The compilers generate instructions from the high level language code. Then you can observe the registers are assigned, but the number of register is limited in the RISC-V processors. Actually, the number of registers is defined by instruction set architecture. So in RISC-V, the number of registers is 32. Okay, so the number of registers is limited, so compiler needs to manage how registers are assigned to instructions. Okay, so register optimization is important. Okay, okay. Also, this slide shows the different uh, the load instructions and store instructions. Okay, so I mentioned that there are two types of memory instructions: the load instructions and store instructions, right? So, but we can just specify the size of data transferred by the load instructions and store instructions. So so as you can see, if the load instructions transfer byte data, then we can use LB. So B means the byte. Okay, byte is 1 byte. And then if the half word data is transferred, what is the half word? Half word is the 2 byte, right? Then we can use the LH. The data size is a word, then we can use LW, so load word. But also you can find the LBU and LHU. So I will explain later. So, but this U represent unsigned. Okay. And store instruction is a store byte, store half word, and store word. So there are different kinds of load and store instructions, but with this load and store instructions, we can specify the size of data. Okay. 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 So then I will explain about the signed and unsigned numbers. Okay. So what is signed? Well, unsigned numbers. So signed means that the number has signed bit, right? So signed bit can be plus and minus. Okay. The unsigned means that all numbers are positive numbers and zero. Okay. Zero and positive numbers. Okay. This is the unsigned numbers. Then let's see how computers represent signed numbers and unsigned numbers. So as I mentioned, the computers handle binary numbers. Okay. And then so we we learned how binary numbers are represented. So it means that we can calculate the magnitude of binary numbers. Okay, so like the decimal numbers, it's digit of binary number represent the magnitude of the digit, right? Like the 2 to the power of 0, 2 to the power of 1, and then 2 to the power of n minus 1. For the n-bit numbers, then n-bit binary numbers, then the magnitude of binary numbers can be represented using this equation, okay? Because each digit represents the magnitude of power of digit number, right? But so unsigned number. So unsigned number means that, as I mentioned, these numbers include 0 and additive numbers, right? So it's a range of unsigned number is 0 to 2 to the power of n minus 1, okay? So, and then unsigned numbers can be represented like this. So if we use the 32-bit, then this is the range of a 32-bit number, and then this is the range of 64-bit unsigned number. Now, how about the signed number? Signed numbers is so we use the two's complement number system. So computer systems, we can represent the signed numbers using two's complement number systems, right? So two's complement number system, the MSB of this two's complement number represent the sign bit. And then if the sign bit is 1, then it means the negative number, right? And if 0, it means positive number and 0, right? And then in the two's complement number system, the MSB, you can find that the minus sign for the MSB. So we can calculate the number. So this we can translate the two's complement number to the decimal number using this equation. And then the range of this two's complement number is like this. So minus 2 to the power of n minus 1 plus 2 to the power of n minus 1 minus 1. So compared to the unsigned number, so you can find that this is n minus 1. Okay? Okay, so you need to know that MSB is the sign bit in the signed numbers. Okay, so it means that, so if the MSB is 1, it means it's a negative number, right? So actually bit 31. So we are learning about the 32-bit computer system, right? So in the word data, bit 31, this is the MSB is a sign bit. Okay, so 1 is for negative number, and then 0 is for non-negative number. So it means 0 and positive. Okay, so in a two's complement number system, so 0 is all zeros, and then all ones is minus 1, and then the most negative number is the 1, 0, 0, 0, 0, right? So obviously this is the minus 2 to the power of n minus 1, right? And then following numbers is a positive number, but all these positive numbers are zeros. So this is the most negative number. Now what's the most positive number? So this is 0, okay? And then all positive part are ones, okay? So negation. So sometimes we can change the sign bit of a variable like this. Then how? In a two's complement number system, then actually in order to change the sign bit of a variable, then we firstly invert the all bits of a variable and plus 1, right? So this is the minus a. So it is because so it means it's the inversion of all bits. If this is the binary some binary data, if x plus inversion of x is the all ones in binary. So what is this one? This number is minus 1. So negation x plus 1 equal minus x, right? So this is the example. So negate plus 2. The plus 2 is the 0, 0, 0, 0, 0, 0, 1, 0. So in order to make minus 2 from plus 2, so we firstly invert all digits. So it is the 1, 1, 1, 1, 1, 1, 0, 1, and plus 1. So it becomes the 1, 1, 1, 1, and 0. Okay. So this is the signed number system and unsigned number system. Okay. So then you need to also know about the sign extension. So sometimes actually the number of digits, for a certain number, for a certain binary number needs to be increased. So this is the extension. Okay. Then if a number is the unsigned number, then we can just add zeros. Okay. So for unsigned number system, we can just extend with zeros, right? But how about the signed number? The signed number, then we can just repeat the MSB. So this is the example. So this example shows that we want increase the number of digits from 8-bit to 16-bit data. Okay. So in order to extend the number of digits, then if the number is the plus 2, then you can find that MSB is 0, right? Obviously. So in this case, so we can just repeat the 0. Okay. So this MSB, so it's the sign bit is repeated. So minus 2, you can find that the MSB is 1. It means the sign bit of this number is minus, right? So in this case, 1 is repeated. So you know the bin number is increased. So this is called the sign extension. So you need to remember that if target number, so if the data is the unsigned data, then we need to apply zero extension. So it means regardless the MSB of this number, for the unsigned number, then we just add zeros, okay, in order to increase the number of digits. But if we are using signed number system, then we need to apply sign extension. What does that mean? It means the MSB is replicated. Okay. So you can find that. So LB. So it's in the load instruction that you can observe LB and LBU. So why? So why do you need to distinguish the signed number load and then unsigned number load? So it is because, so think about this. What is a load instruction? The load is that this is the memory. And then load instruction, just to read data from the memory and then transfer this data to registers. Okay. But what is the size of a register? The size of a single register is 32 bit. RISC-V 32i. So this is the 4 byte. But think about the LB, the load byte. The load byte just read byte data from the memory and then transfer this data to the register file. But in the register, the size of a register is 4 byte. So in this case, we need to increase the number of bits for this data. Okay. Then we need to fill this register file using the extended bit extended data. So if this number is the unsigned number, like the 11111111, so what is this number? This number is it's a 127, right? Right? No. 255. It's 255, right? So this is the unsigned number. This is so 255. And then if this number is allocated to a 32-bit register, then we need to increase the number of bits. Then if this number is the unsigned number, then we need to fill the remaining part as 0 using 0, right? This is the 0 extension. So if we use the LBU, okay, then it indicates that, oh, this byte data is unsigned data, unsigned number. So when this data is allocated to a register, then 0 extension needs to be applied. On the other hand, if we just use the LB, then it means that this is the signed data, okay, signed number. So when this byte data is allocated to a register, then we need to apply sign extension. So that's why for load instructions, the LB or LH has the sign extended load or 0 extended load, like LB or LEU. So you can observe that signed load is the default load. Okay. So if this byte load handles unsigned data, then we need to use the LBU. Okay. So actually, because the computer systems can handle the signed data or unsigned data, then also you need to think about this sign extension or 0 extension. Okay, so this can be very critical. So sometimes instructions can handle unsigned data, or sometimes instruction can handle signed data. Okay, for the different cases, we need to apply different sign extension approaches. Okay. Okay, so let's see how to generate constants. So I mentioned that in our program, so we frequently use small constant, right? Small constant numbers. So, and then, so we also learned that in RISC-V instructions, RISC-V includes immediate type instructions, right? And then this immediate type instructions include immediate data. Okay, it's a small constant data. Okay, so then let's see how we can generate constant in instructions. Okay, so we learned about the add I. So add I is the add immediate. So using this add I, so we can easily create the small constant number. So this is the example. So int a equal minus 372. Okay. So, but in the add I, so add I can handle 12-bit immediate number. And then this immediate number is the signed number. So like the add I, x1, x2, and immediate, and this immediate number represent the 12-bit signed number. Then what is the range of this number? The range of this number is 2 to the power of 11 minus 2 to the power of 11 minus 1. Okay, so what is this number? It's minus 2048 to 2047, right? Because 2 to the power of 10 is 1024. So minus 372 is in the range of this number. Okay, minus. Okay, so we can so let us assume that the S0 includes the variable A and S1 includes the variable B. So in this case, we can easily store the minus 372 in S0 using add I, because this number is in the range of this range. And then also int B is the A plus 6, so you can easily represent this statement using the add I, S1, S0, and 6. Okay, so it means the S1 equal S0 plus 6, but S0 includes the number in variable A. Right. So for the small constant number, so we can easily create a small constant number using add I. Okay, so but you need to remember that the add I, so this immediate number just handles the 12-bit signed number. It's a signed number, right? But sometimes we can handle very large number. So in this case, we can use the, so for example, we want to generate the 32-bit constant. Okay, so in this case, we can use the LUI instruction. Like LUI represents load upper immediate. So in order to generate the 32-bit constant, then we can combine LUI and add I. So actually, we use LUI for define upper 20 bit, so upper 20 bits, and then we can use add I for the lower 12 bit. So this is the example. So int a equal it's a hexadecimal number, FEDC, and then A765. So this is a very large number, right? But in order to represent this number, so we can combine LUI. So LUI can represent the upper 20 bit number. So upper 20 bit is this number, right? No. This amount of number is upper 20 bit. And then this numbers is the lower 12 bit. So using LUI, the upper 20 bits is stored in the S0, and then using add-I, then lower 12 bit is added. So when the LUI is executed, so S0 is held in, no, S0 is holding the variable A. So S0 is the 32-bit register file, right? So for the upper 20-bit, it's like FEDC8 is stored in the S0, okay? But lower bit includes the 000, okay? Then using the add-I, then the S, it means the S0 equal S0 plus 0x765, right? So 765 is added. So then what is the final result? Final result is the FEDC8765. Okay, so S0 can hold this number, right? So using the LUI and add-I, then we can create very large constant number. Okay, we can store these large constant numbers in a register. But you need to remember that add-I handles the 12-bit data, then 12-bit immediate data, but this is the signed number. So which means that when this add instruction is performed by add-I instruction, then actually add-I applies sign extension. Okay, so I will show the example. So this example shows that we want generate this number, this large number, right? But it's different. So in this example, the lower 12-bit is the 765. So what is the 7? This 7. This is the 0111. So the MSB is 0. But in this example, the lower 12-bit is the EAB. And what is E? E is the 1110. So you can find that this is the 1, right? So it's MSB. And then the add-I is calculated in a CPU, then CPU performs sign extension. Okay. So because the MSB is 1, then actually it extends this number as the 1111 and 1110. Okay, like this one. So actually it performs this operation. So when the sign extension is applied, then EAB becomes the FFFFF EAB. Okay, because the sign extended. No. So what's the problem? In this case, if we just write the code like the LUI and then this is the upper 20-bit. So FEDC8 and then add I and then it's the EAB. So EAB and plus then it will generate the incorrect result. Why? So it is because when EAB is added in a RISC-V CPU, the RISC-V CPU applies sign extension. So if the sign extended, then it becomes the F, 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 and E, A, B. What's the problem? So like F, E, D, C, and 8, 0, 0, 0, then it will generate the, so this is the EAB, right? But for this point, then actually F, 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 F is the -1. So it is the, it becomes the FETC7. So it generate wrong. It generate incorrect constant. So actually, in order to generate this constant number, it should be 9. So because I mentioned that FFFFF is a -1. Okay. So it, this is the EAB, and then in this part is the FETC8. Okay. So in order to generate this number, then the first LUI is the FETC9. Okay, not 8. So, and then we can store the correct number in S0. So this is important. Okay. So when a compiler create instructions, then compiler needs to consider this case, right? Okay, so this is the some examples of signed extension and unsigned extension. So signed extension and zero extension. Okay, so when we handle signed data, then when this data is extended, which means that the bit number is increased, then you need to remember that we need to apply sign extension. Okay. Okay, so let's see the another type of instructions. So logical and shift instructions. So what are logical instructions? So our high-level language code also includes the logical instructions such as the bitwise AND, bitwise or exclusive or, the negation is not. Also, these language, this code also supports the shift right, shift left or shift right operation. So bit shift left, the is bit shift operation like the shift left or shift right. So this is the example. So C, C, we can use this operator to perform shift left, okay, and then shift right is this operation, and then we can also use the AND or exclusive or and negation. Okay, so Java also includes the similar operators, right? So in RISC-V also needs to support these logical operations, right? So shift left, RISC-V, so includes the SLLI, so it's a shift logical left, shift left logical immediate, and then for the shift right, the RISC-V has SRLI. So it means the shift right logical immediate. Okay. And then for the bitwise AND, RISC-V has the AND operation, AND instructions, and or AND I, or, and then for the bitwise or, RISC-V has or instructions, and then also bitwise exclusive or, RISC-V has the exclusive or instructions. And then for the bitwise not, like negation, RISC-V does not have not operations, bitwise not, but we can easily implement bitwise not using exclusive or instruction. So this is the example. So this is the AND, is the OR and the exclusive OR, and the S1 and S2. So AND means that bitwise AND means if the all bit is 1, then result is 1. Otherwise, it's a 0. Okay, you can find the bitwise AND operation here and bitwise OR. If the one of bits is 1, and it becomes 1, like here. And the exclusive OR performs the exclusive OR operation, like 0, 0 is a 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, right? So it means that if the two bits are different, then the result becomes 1. Okay, so this is the useful operation. So we can use the AND instruction for the masking bit. So which means that, we want extract this number, then we can just end this number and the 11111 F. Okay, then we can just extract this a certain digit of numbers. And then bitwise OR is useful for combining bit field. So this is the example. We can just combine this number and this number, right? So you can find the 0000 here. It becomes the 0. For the bitwise exclusive OR, and it is useful for inverting bits. Like A exclusive OR -1 is the not A. Okay. Okay. So this is another example. Is so this is the example of the logical instruction, and this is the example of immediate and immediate OR and immediate exclusive OR. Okay, so and then this is the format, and then you also like the immediate add instruction. You can find that when the immediate is included for some logical operation, the immediate number is sign extended. So we need to apply sign extension for immediate number. So even in the MSB is 1 for this example. So 11111 is included. Okay. So this is the result. Okay. You need to remember that when the immediate number is included in any operation, then we need to apply sign extension. Okay. So for the shift bitwise bit shift operations, the RSIC-V supports the SLL, the shift left logical, SRL, the shift right logical, and then SRA, the shift right arithmetic. So this is the equivalent to C code. Okay. Shift left logical is the shift left and fill with 0. So it means that so if the 1111 is shift left logical is applied to 1111, then it becomes like the 1100. So 0 is added. Okay, so shift left, shift right, and then if the direction is opposite, like a shift right, 1111, then 0 is added. Okay, this is the shift right. But we also need to consider signed and unsigned number. So we can, for the unsigned number, then we may need to apply shift right arithmetic. Okay, so it means it's a 1111 is shift righted, then is shifted right, then and then but if we just apply SRA, then it becomes the 1111. So instead of 00, the MSB is just replicated. This is the SRA. Okay, so you can just remember these different types of shift instructions. Okay, okay, shift instructions also includes the immediate instructions like SLLI, SRLI, and SRAI. So shift amount is immediate between 0 to 31 because you know the register size of a register is 32 bit. Okay, so this immediate should be 0 to 31, between 0 to 31. Okay, okay. Also shift amount is in lower 5-bit register. Okay, here. Okay, so this is the some so I explained about the some logical and shift the logical instructions. Okay, and then also I explained about the immediate values. So which means that we can just handle some immediate values. Yeah, like so I mentioned that. So immediate values can be included in the RISC-V instructions, but you need to think that you need to remember that these immediate numbers are signed numbers. Okay, and then if the immediate numbers are included in operations, then we need to apply sign extension, right? So you need to remember this, okay? Immediate number is the signed number. And if the signed number, if we just increase the number of bits for a signed number, then we need to apply sign extension, okay? Okay, so I will stop here, and then in the next class, so uh, we will learn about the control instructions like branch instructions and jump instructions. So before the next class, so please watch this recorded video. So okay, okay, it's important. Okay, okay. So thank you for watching this video, and then see you in the next class. 감사합니다.